Okay, so in the previous class, we were mainly discussing about how we can go about with object tracking, right? And we saw that there are broadly two methods. One is the tracking by detection, where you have several frames, and what you do is for each of those frames, we apply an object detector, okay, which detects the object of interest, whatever object we are looking for. And once we have those objects detected, those locations would be linked together in order to find a particular track, right? And we also saw the case of multiple objects, or if there is a case of an object entering the scene later, or the frame later in the video sequence, or when the object is leaving later in the video sequence. Then after that, we just started off with tracking using matching. Okay, and we were discussing in the previous class that there are two types of matching. One is the okay, so one is the summary matching, and the other one is the optical flow based matching. So we'll in today's class we'll see in detail about the summary matching for object tracking, and then later we'll discuss the optical flow. Okay, so in summary matching, okay, or tracking using the summary matching, what we do is, as discussed earlier, we create a summary representation. Okay, so in the sense, in the previous case where we do our tracking by object detection, okay, what we are doing is when we are trying to compare the two frames, okay, in which the object has been detected, what we do is we take a measure of SSD, which is basically the sum of squared difference, right? So in that, what we do is we take different frames and we do a pixel to pixel comparison over there, right? Now in summary matching, what we are doing is we are not trying to match pixel to pixel in every frame. We are only trying to create a summary of the object of interest, or the region of interest rather, and then we try to kind of match those summary representation rather than those individual pixels. Now how that helps is, see, when you are having individual pixel comparison, there is a chance that, let's say, in whatever video sequence that you are considering, or whichever video sequence that you're playing, sometimes there may be a chance that there could be some kind of a motion blur, okay, in which, so if you have such kind of a motion artifact or a motion blur, what happens is the pixel intensity changes, okay, or let's say you're having some kind of illumination variation in the background, okay, while the video sequence is going on. So what happens is, because of the illumination variation, the pixel intensity could change even though it is the same object. So let's say I have a frame here, okay, and let's say I have another frame here, both of which have got the object of interest which I'm, trying to track, okay. But let's say in this frame I have a particular intensity, and here's let's say the light suddenly dimmed out, or the light in the surrounding has suddenly brightened up, or so on, okay, some kind of an illumination variation. If that has happened, or an exposure variation basically, now if that has happened, what happens is the pixel intensity values of this object would change, right? Even though, I mean, it would change with respect to the intensity illumination variation that has occurred. So even though it is the same two objects away, I mean, it is the same object but between two different frames over here, when you're calculating SSD, it would give a very large difference, because basically the pixel intensity is different. But if you have a look at it, in this case the objects are actually the same, okay. So that is one disadvantage when you're working with, a pixel to pixel comparison, right? So a better approach would be to, instead of taking a pixel to pixel comparison, you can go with just a summary representation, okay. That means you take this region of interest which is very close to the object, so I'm not just looking at the object alone, I'm trying to form of a small bounding box across the object, okay, so which has got a little bit neighborhood area too. So once I have that object of interest or that region of interest or the bounding box, right, I can create a summary. Okay, now those summary representations, it can be any kind of representations. I'm creating a kind of summary to represent the whole patch, okay, over here. And in the next frame, I'll be looking at neighborhoods, different neighborhoods which are nearer to this location. And for each of those neighborhoods, I try to compare the summary representations and see how close the summary representations are. So by comparing summary representations, what I'm doing is I'm letting go of the pixel to pixel comparison. Rather, I'm taking the whole picture into account. That is the pixel information which is present in the whole, in the whole patch into account rather than a pixel to pixel comparison. Okay, so this is a main idea of matching using summary or tracking using summary matching. Okay, so let us see over here in this particular figure, right? So in this figure, what we see is that we have, let's say we are considering this particular player, right? So sorry about that. Okay, so let's say this is the particular neighborhood which we are considering for this particular player, right? So what I'm doing is, instead of doing a pixel to pixel matching with the next frame, I take the summary of this whole. Okay, so the summary will discuss, what could be a good summary representation. But let's say I'm having some kind of a summary representation for this particular picture or this particular patch here, right? So if I have the summary representation for the next frame, right, I will be just comparing with this particular summary. So these are some of the results which have been obtained from using the summary matching for this particular video sequence. Okay, and if you observe that, in each of the frames, the patches which have been identified, you do see that it is the same person. But in some of the patches, like for example over here, we see that there is, the person has been identified, yes, but there are, the position of the person within that frame is different. Okay, so in this particular case, if we were doing a pixel to pixel comparison, the SSD would have shown a large value. But since here it is just the summary which has been, compared, the summary representations of the different patches which have been compared, it would prove advantageous, okay, over the pixel to pixel comparison. Okay, so as I said again, in the previous method, if we were doing an object detection or tracking using object detection, what we would have done is we would have first tried to apply a translation transformation, and we would have tried to find out what is the translation transformation that fits best, right? And then we refine it further using the affine transformation. Okay, and the similarity measure which was used in the previous case for tracking using the detection or detectors was the SSD, or the sum of squared difference, right? Okay. Okay, so here what we'll see is a step-by-step procedure of how the matching or tracking using the summary matching works. So what we do is, in the first frame, okay, we identify a domain of interest. So what we mean by a domain of interest is, as we saw in the previous picture, right? You have a particular neighborhood, okay, which is taken around the object of interest. Now that would be my domain of interest, or I can just call it my region of interest also, it's the same. So what we do is, in the first frame, we identify what is this domain of interest for us, okay? And then what we do is we try to represent this using the summary representation, right? So what we do is, why we need the summary representation is so that in the next frame, okay, when we are going to the next frame, we can just use these summary representations for the matching, okay, or to make a comparison between the different neighborhoods which are present in the next frame or successive frames. So yeah, so what we see here is that as a good summary representation, okay, we can usually, or what we use is a simple technique that we use is a histogram representation. So histogram representation means, we have already discussed this earlier. So it's nothing but what you're plotting is the different pixel intensity values would be plotted here, and in this y-axis it would be what is the number of pixels having that particular intensity value. So let's say you have a 256 intensity or an 8-bit image. If it's an 8-bit image, the total number of pixel intensity levels that you have is 256. So the lowest one would be 0 here, and the highest intensity you have is 255. So basically in the histogram, what it does is, if it's an 8-bit image, you will have in the x-axis all the values between 0 to 255. Okay, and corresponding to each of these values, it will 0, 1. Okay, corresponding to each of these intensity values, it will try to plot how many number of pixels are present within the particular image, right? Now, in this case, we are using histogram for the summary representation of the domain of interest. That means, see, this is the domain of interest that we have along with the object, okay? But this is part of a bigger, image frame. So let's say this is the image frame of the particular video sequence. Now, we are not calculating the histogram of the whole thing. Okay, we are just calculating the histogram for this particular domain of interest that we have, right? So for this particular domain of interest, we calculate the histogram, or we compute what is the histogram, and that histogram will act as the summary representation for us. And as I said, histogram would be nothing but it is a plot showing what is the frequency or the number of pixels having a particular or a specific intensity value. Okay, so once the histogram is computed, so let's say this is the first frame you have, right? And in the first frame, you have first identified a domain of interest, okay, or an object of interest. Now, what we do is we make a summary representation, or let's say we are making a histogram here, okay, and let's say the histogram is having some kind of a distribution over here, right? Now, what we do is that in the next frame, okay, so let's say you have a next frame over here, right? Okay, so around this particular object of interest or the domain of interest, we will look for different neighboring patches. Okay, so one patch may be here, another patch may be, let's say here, or another patch may be here, or so on. So along the vicinity or along the neighborhood of this particular patch, right, we will, in the next frame, we will look for similar, patches, okay, of the same size. Now, after looking for these patches, what we do is, for each of these patches, we again calculate what is the histogram. Okay, so after calculating what is the histogram of each of these patches, okay, what is done is basically we look for a matching between the different histograms. We try to match, or we try to find how similar each of these histograms are with respect to the original one, right? And the histogram which shows the maximum similarity to the first frame or the previous frame would be selected as the next position, okay, or we can say that the object, it has moved to this position. So let's say this is the particular let's say position or the neighborhood where it showed a similar, the highest similarity in the histogram. Then what we say is that, okay, the object which is present over here in the first frame has moved to this particular location in the second frame, and so like that consecutively in all the successive frames, we adapt the same method, okay, wherein we take the domain of interest or the region of interest, calculate the histogram, okay, which is basically acting as a summary representation, and then in the consecutive or successive frames, we look for neighboring, neighboring regions of the same size, and we calculate the histogram and then try to match them. Okay. So yeah, so this is the basic working principle of the tracking by matching the summary representations. Now, why do we use this histogram? Okay, or what is the advantage of using the histogram? So as I told earlier, when you're using the histogram, what it does is it plots how many number of pixel intensity, how many pixels are present within a particular or having a particular intensity level or value, right? So as I said earlier, okay, let's say you have a particular, distribution, okay, somewhat which looks like this or so on, okay. Now, if you just try to plot the whole thing, you will kind of get an envelope for the histogram, right? Now, let's say there was some kind of an illumination variation, or there was some kind of a motion blur, because of which the pixel intensity values have changed slightly. Okay, so I'm not talking about a very large difference in the pixel intensity values, but let's say due to some external factors, it has changed the values slightly. Then what happens is, let's say from this bin, okay, if there is some kind of intensity variations, what happens is, some of these pixels or one or two of these pixels may go to the neighboring bins. It may go to this bin, or it may go to this bin, or so on. So what happens is, when you have these slight variations, there would be the pixels would move to the neighboring bins, depending upon how the pixel intensity variations has taken place. But what you'll observe is that the overall envelope, okay, or the overall shape of the histogram would not be affected much. Okay, so because it is not affected much, the histogram, the basic envelope is not affected much. What happens is, when you're trying to match with the previous frame or the first frame, it would show a high similarity. Okay, so that is that is one advantage of using the histogram representation, because basically it is robust to changes in the pixel intensity values. Okay, so what we can say is that two histogram will be similar only when the two patches have similar number of similar structures in them. Okay, so when you have similar number of similar structures itself, what happens is, this particular shape or the envelope that you have for the histogram would kind of look similar. Okay. So yeah, so that's about using histogram representation as a summary representation. And because it is not a pixel to pixel comparison, and because the overall shape of the histogram remains more or less the same, with slight changes in the pixel intensity values, it is a good choice for the summary representation, and we can go ahead with histogram matching. Okay, so next what we'll do is, we'll just try to understand another topic, which is mean shift theory. So first we'll try to understand what is mean shift theory, okay, and how it works. And then later we'll see how that can be used for similarity matching and tracking applications. Okay, so first let's start with what is mean shift theory. Okay, now this mean shift algorithm was first proposed in this particular paper. Okay, so this is a paper, a robust approach towards features space analysis, which was published in 2002. Okay, and you can have a look at the paper if you want to know the details. Anyway, the overall summary of how the mean shift theory works would be discussed in today's class. Okay, so yeah, so let's just try to understand in brief what is, or how does a mean shift algorithm work, and then we will see some of the mathematical concepts which are associated with this. Okay, so let's say we are given some data points in 2D. Okay, so this is a set of data points that we have, and this is present in 2D. Okay, which means that you just have two parameters, let's say, or two coordinates for representing each of the data points in this particular example. But in reality, you can have n dimensional data points also. So for here, just for simplification, we'll just assume data points in 2D. And what we want to do is, we want to find the densest region. Densest region means the region which has got the maximum number of data points crowded within it. Okay, the densest region. So the mean shift algorithm would help in finding this densest region. Okay, so over here, when you look at this particular diagram, what we see is that we can easily see that yes, it is somewhere over here that you have the densest region, right? Now how can we develop an algorithm, or how can this particular mean shift algorithm help in identifying automatically what is the, or where is the densest region? That is what we'll be seeing. Okay, now these data points that we are considering over here, right? Now these data points could be the result of some other image processing or computer vision techniques. Like for example, let's say you have taken the gradient of an image, and maybe you have derived at these data points. It could be it could result from maybe taking the gradient, or it may be just taking the pixel intensity values, or it may be taking the color information, or it may be by taking the texture information within a particular region, or so on. So these data points, it can be a result of any of these techniques. Okay, but basically what these data points represent would be the particular object which is present in the image, right? So what we are trying to do here is we are trying to find the densest region. Okay, so for that, how do we go about this? Okay, what we do is first we will randomly we will select an initial region of interest. Okay, so this region of interest could be anywhere. So let's say the region of interest which I'm initializing is the one which is shown in blue. Okay, let's just assume it could be anywhere within the whole data distribution. So the first step here would be we randomly select the region of interest, and then we identify its centroid. Okay, in the sense the center of the circle and the radius of the circle. Okay, so basically we are more concerned with the center of the circle. We'll see why later, right? So we have this particular circular region of interest with a center and a radius, right? Now what we do is within this circular region of interest, we try to look at all the data points, and we try to calculate what is the center of mass of all the data points, or after considering all the data points within this circular region of interest, right? So what happens there is that when we are calculating the center of mass, it will definitely move towards the region where it is having a denser, or where the data points are more crowded, right? So in this particular example, what we see is when we are calculating the center of mass, this orange color over here, this represents the center of mass for this circular region of interest which we have considered, right? So this center of mass, now why is it deviated from this centroid, or the center of the circular ROI, by this much amount? This is because if you're looking at all the data points within the circular region of interest, what we see is, if you look at this side, there are not many data points, right? But if you're looking at the right hand side over here, what we see is that there are many data points which are closer together, right? So when the center of mass is calculated, it would tend to move more towards the denser region. So it would be somewhere over here, okay, as shown in this example. So that is our second step. Now, next what we are doing is we are trying to move the center of the circular region of interest towards the center of mass, which has been identified in the previous step. Okay, so what we're doing is we're trying to move the whole circular region of interest with the center coincided with the center of mass which was estimated, right? So what happens there is, now you will have a new circular region of interest with the center which is present at the center of mass of the previous case. Okay, now like that we can keep continuing that. Okay, so this particular shift over here, that is what we are doing is we are shifting the centroid of the circular region of interest towards the center of mass. Okay, so that it moves towards the densest region. And so this particular vector which is formed right between the center of mass and the center of the circular region of interest can be called as the mean shift vector. Okay, so it is called as a mean shift vector because you do have a magnitude, you do have a direction in which it is moving. Okay, and it is shifting towards the mean or the center of mass, and so it is called as a mean shift vector. Okay, so what you do is you calculate the mean shift vector. Okay, and you move the center of the region of interest towards the center of mass. And once it moves towards the new center of mass as shown over here, okay, you now get a new region of a circular region of interest with the center coincided with the previous center of mass, right? Now next what happens is you will again look at all the data points which is present within the circular region of interest, and then again try to calculate the center of mass. And what you will see is that again you will have the center of mass somewhere located towards this region, because you see that there are more data points which are crowded or which are dense, which are located close together, okay, in this particular region. So the center of mass would be identified, okay, towards here. So you'll see that the center of mass is over here. So now in the second iteration, again you have found the center of mass, right? And from there you can find out what is the mean shift vector. Okay, and we'll see that this is the direction in which it has moved. Okay, and then now in the next step what can be done is, again, this center of mass can be you can shift the circular region of interest in such a way that this center of the circular region of interest coincides with the center of mass which has been estimated, right? So like this, what we are doing is we are keeping on updating, or we are with iterations you're keeping on moving towards the center, right? So now what happens is, yeah, you have it like this, it is moving, right? So again in the next iteration it keeps moving towards the center of mass. Again this is recalculated and it keeps moving towards the center of mass. Now what happens is there would be a stage, as the iterations keep on moving, there would be a stage where the center of mass which was calculated in the previous step, okay, or the current center of the circular ROI and the center of mass which has been estimated in the current step will be the same. Okay, so until and unless we reach this point where the center of the circular ROI coincides with the center of mass, right? That is when you stop the algorithm, okay? And that particular location would be the densest point, or the location of the densest region of the particular data distribution that we are considering. Okay, so I hope that procedure is clear here. So as I said earlier, what we are doing is we are basically trying to move the center of the circular ROI towards the center of the mass, right? So in the final iteration, what happens is when the center of the circular region of interest and the center of mass are coinciding, what happens is then the mean shift vector becomes a null vector. Okay, because there is no more shifting, or there is no more difference between the 2 points. So this particular method, what we see is this particular method, even though you initialize it anywhere. So what we first assumed was that, let's say the circle was somewhere over here, or so was what we first assumed. So even if it is initialized anywhere else, let's say it was initialized in this corner, or in some other place over here, or maybe this particular corner, or so on, irrespective of wherever it is initialized, what we see is that through the iterations it keeps coming to this particular densest region itself. So here here, if it is like, for example, over here, the direction would be, towards this side. Or if, let's say, the initialization was somewhere over here, then this would have been directed like this over here. Okay, so wherever be the initial contours or the initial region of interest that is being, considered, it wouldn't affect the mean shift algorithm where it finds the densest region, because in all the cases what it does is it will just calculate the center of mass and keep moving towards that to find or to reach till the densest region. Okay, so what we're doing here is what is given to us is some data points, right? So we have some data points within a data distribution, and as I said, these data points, it can be the pixel intensity values of the original image itself, or it can be the data points which have been derived from finding the gradient or the texture of the particular image, or of the particular object of the domain of interest for us, right? And in the mean shift algorithm, what it does is the task here is to estimate what is the exact location of the mean of the data, okay, by determining the shift vector from the initial mean, right? So initial mean, in the sense, we initially just randomize, or we randomly select a region of interest, and from which we keep calculating the center of mass and keep shifting and moving it towards the denser regions. Okay, so here let us see some mathematical details of the mean shift or vector algorithm. So if we just have a look at this equation over here, what we see is we have mh of y, which is basically the mean shift vector that we are considering, okay? And h is nothing but the circular region of interest, or the, this particular circular region of interest which we are considering is represented by h, okay? And m is a mean shift vector, right? Now it is given by 1 by nx sigma I is equal to 1 to nx xi minus y naught. So here y naught here is basically the initial estimate that you have, okay? Or let's say you're looking at successive frames. So when you're looking at successive frames, it would be the previous estimate of the center of mass that you have, right? So you have y naught, which is the previous estimate of the particular center of mass, right? Now, what we are doing here is we are basically trying to find out what is the difference between the previous estimate of the center of mass and the present estimate of the center of mass, right? So these two together will then give me what is the vector towards which it should be moving, right? So let's say this is the y naught here. This is the previous estimate that we had for the center of mass. And what we're doing is for the current, so we know that the circular ROI has then shifted to according to the previous center of mass, and then again it is calculated. So again, when it is calculated, let's say y1 is a new center of mass which has been obtained. So then what happens is the mean shift vector is defined by combining these 2 points over here, or these 2 center of mass over here, okay? And that is what is basically shown in this equation 2. So when I'm saying the present estimate, how that is calculated is what we take is basically the mean of all the data points, okay, which is present within the particular circular region of interest, and the data points you can represent that by xi, okay, and assuming that there are nx points within the particular region of interest that we are considering. And another thing which as I said earlier, when we, in this example, we are just considering a 2D vector for the data points which are present, but the data points can be any dimensional vector. It can have any dimensions, okay. Now, mean shift vector always points towards the direction of the maximum increase in the density, right? Because each time, for each iteration, what it does is it keeps moving towards the denser regions. So when you're moving towards the denser regions, what that means is wherever you have a maximum increase in the density, okay? So irrespective of what is the initialization, this would happen. Okay, so in the previous slide, in the equation which we saw, right, what we did was we just took an average of the different data points which is present in the circular region of interest in order to find out the present estimate for the center of mass. So, a better approach would be to consider a weighted mean shift vector. Okay, so in weighted mean shift vector, what we do is instead of assigning equal weights or instead of assigning uniform weights, both equal weights and uniform weights means the same. So instead of applying that, what we can do is we can apply different weights to each points. Okay, to further help with movement towards the densest region to make the algorithm much more efficient. Okay, so what we're doing is by assigning weights to each different data points, we are taking the weighted average instead of taking just the average. Okay, so as you see in this particular example, in the case of a weighted mean shift vector, what you say is here in the numerator, if you have a look, this wi basically represents the different weights, okay, corresponding to the data point xi. Okay, so what we're doing is basically we're just taking a weighted average as the present estimate. Okay, and then the difference of that with the initial estimate would give me what is a mean shift vector. Okay, so when I'm taking these weights, okay, how do you assign the weights, or how do we decide what are the weights which has to be assigned, right? So in order to determine the different weights, you can make use of various kernels. Okay, some of the kernels that you can be familiar with are the uniform kernel, the Gaussian kernel, and the Epiniknov kernel. Okay, so uniform kernel means it is just as discussed earlier, where you may just give a weight of 1 to all the data points. Okay, or you can give another weight to, but it is uniform throughout the whole of the data points. Okay, so it basically, when you're taking the average, that basically becomes just a uniform weighted, it's a uniform weighted average. In the sense, it is just uniform there. That is all we are considering, that all the data points have equal contribution towards finding the center of mass. Now, if you're looking at a Gaussian kernel, you will see that the weights are assigned in such a way that it follows the Gaussian distribution, right? And you also have the Epiniknov kernel, okay? And there are other kernels also which could be used. So basically, the advantage of using a weighted mean shift vector would be, a better efficiency in the algorithm. Okay, it could help with reaching with the denser regions in a faster manner. Okay, it would be more efficient. So, discussing some of the properties of the mean shift algorithm. So the first property is that the mean shift vector points towards the direction of the gradient of the density estimate. Or you can also say the mean shift vector points towards the direction of the maximum density. Okay, so what that means is it keeps moving towards whichever is the denser regions, right? And another property that you have is that it is an iterative process, right? So what happens is it is computed iteratively for finding out what is the maximum density, and the iteration stops when you have the present center of mass coinciding with the previous center of mass. Okay, now why so we have understood what is the mean shift algorithm, and what we understood is that the mean shift algorithm can be used to find which is the densest region within a particular data distribution. Now, how is it exactly used, or let us see how it can be exactly applied. Okay, so one advantage or one use of the mean shift algorithm is to find the modes of a probability density function. So what do you mean by modes is basically the peak in the PDF. Like for example, let's say you have a particular distribution. Okay, let's say it's a 2D distribution and something which looks like this. Okay, here it's not a plateau, there is something like this, right? So let's assume it's a Gaussian distribution. Okay, so if it's a Gaussian distribution, what we see is that it will have a particular peak, right? So to identify this particular peak, that can also be called as a mode of the PDF or the probability density function. In this case, it is a Gaussian PDF, right? We can make use of the mean shift. So mean shift would consider this peak over here to be the region of, the densest region within the particular distribution, data distribution that you have, right? Now, when you're talking about probability density functions, some of the examples are the Gaussian distribution, the Poisson distribution, or the Rayleigh distribution, or so on, right? Now, one specific thing about these distributions is that they are parametric distributions. So parametric distributions means that they have certain parameters to describe that particular PDF. Okay, like for example, for this particular PDF, you can have the mean. Okay, so you can represent the mean as well as the standard deviation. Let's say it's somewhere within this. Okay, you have the mean and the standard deviation. Two parameters would be sufficient to describe the whole of the PDF. Okay, so like that, when you have parameters which can be used to describe the particular PDF or the probability density function distribution, okay, that is called as parametric distribution. But all kinds of data distribution that you have may not be parametric. In the sense, it may be something that cannot be exclusively described using just a few parameters alone. So such kind of distributions are called as non-parametric distribution. Okay, it's called as a non-parametric distribution. And what we see is that the mean shift algorithm, basically it helps with giving a representation, or for helping in describing non-parametric distribution. Okay, and we'll also see how that is done. Okay, so why it's important to go with a non-parametric distribution is, so as I said earlier, if you have a parametric distribution, what we are saying is that if you know the parameters, let's say the mean and the standard deviation for a particular Gaussian PDF, you can describe the whole distribution, right? But if you're looking at computer vision applications, okay, if as I said earlier, the data points that you're getting, it may be the pixel intensity values, or it may come from the result of some other pre-processing techniques, computer vision techniques, right? So like for example, finding the gradient or the texture or so on. So these data points that we are getting for that particular object of interest may not, you can't guarantee that it would be a parametric distribution, right? It could be a parametric distribution, it may not. So it is important to go with a method that would help to address non-parametric distributions, okay, or distributions where it may not where you may not have strict parameters that can help to describe it completely. So this is how the mean shift algorithm helps with the study or the description of the non-parametric distribution. Okay, so let's just have a look at this particular example, which you see here, right? So as I said earlier, the mean shift would help to determine what is the peak of the PDF, right? So whatever is the probability density function that you have, okay, it would help in finding this particular peak, assuming that that peak is the densest region in that particular data distribution, right? So what we're trying to do here, when you're trying to estimate what is the PDF of non-parametric density estimation or distribution, we can go about it in two ways. One way is that you can look at the data points. Let's say these are the data points which are given to us, right? You can have a look at the data points and directly try to form an estimate of the PDF representation that you have here. Okay, that is one way which could be done. Okay, another way which could be done is we could make use of the density estimation in terms of the gradient using the mean shift algorithm, which was just discussed now. So in mean shift, as I said, what it does is it will just try finding out the peak of the PDF. So which means what it does is by looking at this data distribution and with random initialization over here, okay, it will keep calculating what is the center of mass, and it will keep moving towards the center of mass, okay, with each iterations, and finally it will stop at this particular place where you have the maximum density, and this place where you have the maximum density would be corresponding to the peak of your PDF, or the probability density function. So by saying that you are finding out the maximum dense region within a particular data distribution, what you're essentially trying to say is, in terms of the PDF distribution over here, right, what you're doing is you're trying to find out, or not you, like the mean shift algorithm is trying to find out what is the peak of the particular PDF, right? So let's say here, this path that you have here is basically the path with each iterations, how the mean shift vector has moved. Okay, so that movement path is shown over here, and finally it has reached the peak, which corresponds to the dense regions. Okay. Okay, now we'll see how we can correlate the particular PDF, or the probability density function that you have, with the data distribution. Okay, so as I said earlier, so let's say you have a particular data distribution and you see that there are regions of low density, and there are regions of medium density and high density, right? So how this translates as the PDF is, as you see over here, that is the peaks of the PDF, or the probability density function, would correspond to the densest regions. Okay, and the peak, or the values over here in the plot, reduces as the distribution of the data also changes, right? So here we see that it is very dense over here, right? And as you move further, you see that the density keeps decreasing, right? So similarly, in this case also, you have the most dense region over here, and then since the density keeps increasing, you have it coming down this way. And if you're looking at this particular point, this is again another local maxima that you have, right? So local maxima in the sense, if you look at this particular neighborhood, this is the region which is dense. Okay, if you're not looking at the whole image but only a particular neighborhood, you can say this is kind of a dense region as compared to its neighborhood. So in that case, if you look over here, it will show a slight peak, but again the peak is not as high as this, because basically the density is also not as high as this. And if you look at other regions, like for example, this particular region, you'll see that the corresponding PDF will show the lowest value, because it's hardly dense, or in this particular example, you hardly have only one data sample or data point in this particular distribution. So this is how we can correlate the data samples which are present in the data distribution with that of the probability density function plot. Okay, so here, as I said earlier, these data points, it could be grayscale intensity values, or some other byproduct of some other computer vision techniques, right? So if it is a grayscale intensity values, I can say that, okay, here at this particular location, you have a lot of grayscale intensities of a particular value, or you can say that there is a high probability of a particular intensity value occurring at this particular location. So that is basically the information which is being conveyed by the probability density function. Okay, So now this one is another visualization. So in this visualization here, the height of all these bars which is shown over here, basically that represents how many data points are present within that particular region, right? So here again, it is just like the previous example. It's just that here it's just a different visualization, that's all. So if you're looking at the different regions of interest over here, okay, it shows that in this particular region of interest you have the highest density, okay, because you have the tallest bar over here, and this is lower density, and here you have the least density, right? And again, corresponding to this, you'll see that here also you have two, just like you have two peaks over here, here also you have two peaks, and here this one is nothing but the lowest or the least dense region in the whole image. So accordingly, that would be the lowest intensity or the lowest values of the particular distribution. Okay. Now, how do we find out a particular mathematical expression for the probability density function? Okay, so we have, let's say we have, seen the data samples over here, and from the data samples you have calculated what is the normalized histogram, and from which you have found out what is the PDF. Now, how do you exactly represent this particular PDF? That is, mathematically, how do we represent is what we'll see next. So for this representation, what you can do is you can make use of the kernel density estimators. Okay, so what are the kernel density estimators? We just see that here. If you look at this particular equation, okay, now this is the equation for finding what is the probability density function with respect to x, a data point x. Okay, and if we see over here, ci is a constant, you have sigma I, which is again the constant with respect to the distribution, and then you have a term x minus mu I, the whole square, right? So here the main idea here is that the higher the number of data points that you have, okay, as shown over here, the higher will be the probability, right? And lesser the data points that you have, lesser would be the probability, right? So it would be kind of a weighted thing that's happening over here. So if you're looking at this particular equation, which is shown here, this ci and sigma I, as I said earlier, they are constant, and the only variables which are changing would be the x minus mu I, the whole square, right? So x is basically the current point that you are considering, because the probability density function of x is given by this equation. So x is the current point that you're considering, and mu I is nothing but the neighborhood. Okay, so mu I is the neighboring points which are present, surrounding the x, which is the current point. So in order to calculate this probability, what we are doing is, here x minus mu I, the whole square, is nothing but, you're trying to find out what is the distance of the current point with respect to the neighboring points. Okay, it's nothing but just a distance measure. So here, if you're looking at this particular term, what we see is that this is nothing but a Gaussian weighting, which is done, right? This is the expression for the Gaussian. So here, the neighboring points which are present nearest to the this particular point x that we are considering will contribute more towards the point as compared to the rest. Like for example, let's say this is the point x that we are considering, and let's say you have some points, okay, near to this, and you have some other points which are further away from this, right? So by doing a Gaussian weighting, what we are trying to say, or what we are trying to achieve here, is that what we are saying is the points which are closer to this point of interest x to us, it contributes more towards the probability density function at x rather than the points which are present further away. Okay, so we are assuming that. So by assuming that, what we are doing is, let's say you have all these points over here, which is the closest to the current point x. Then in that case, these points would be given the maximum weightage. You give a high weight to those points which are nearer to the particular data point, and lesser weight is given to those which are lying further away. So that is why you have this distance measure over here, right? And basically by Gaussian weighting, what is done is this is the kind of distribution that happens. So let's say this is the this corresponds to the location of the data point that we are considering, which is X. Then what we say is that the higher weightage would be given to the points which are present nearby, and the weights keeps decreasing as you have points which are further away from the point of interest. Okay, so that is how you can interpret this particular PDF equation, and what we see is that the equation is very similar to the Gaussian kernel equation. Now, the equation which we just saw right now, you can generalize it for any kernels that you are using. So how we do the generalization is we can write it this way, which is P of x is equal to 1 by n sigma I is equal to 1 to n k of x minus xi, right? So how we are generalizing it is we are basically looking at k. We are not specifying what is k. K is basically representing the kernel, right? The kernel you can use, it could be any type of kernel. So what we are saying is it is basically taking the average of k, okay, of a kernel, which is a function of the distance between the current point and the all the neighboring points that is present, okay, the neighboring points which are basically xi. So in the previous case, in the equation which we saw, what we saw is that this k was basically the Gaussian kernel, right? And that is why you had that exponential term which was used. Now you can also use the Epiniknov kernel, okay, which is given by this particular equation, k e of x is equal to c into 1 minus x squared if the value of x mod x would be less than or equal to 1 and 0 otherwise, and this is how the distribution looks like. Okay, so what we see is that here also there would be a difference in the weightage which is given. Okay, it kind of, the weights kind of reduce with distance, but the reduction in the weight is not as rapid as that you see in the Gaussian. In the Gaussian it's kind of more spread apart, okay, and it's a random decrease, but you don't see that in the case of this kernel. So for the uniform kernel, it is uniform throughout. So if this is the circular region of interest, what we see is that for all the data points which is present within the circular region of interest, it will have a uniform weight, okay, which is given by C. And for the Gaussian kernel, as shown over here, as I said, it is different from the Epiniknov kernel. So in the Gaussian kernel, it's kind of, you have a larger peak, and the weights kind of it is reducing rapidly with distance. Okay. So here the kernels which we have described till now, it is basically the radially symmetric kernel. So what that means is, if you're looking at these, if you're just considering the vertical axis, okay, across each of these, if you're considering the vertical axis, we'll see that it is symmetric about those vertical axis, right? So that is what you mean by radially symmetric kernel, okay, and each of the above three cases was for the radially symmetric kernel, right? So since they are radially symmetric, instead of just writing it as k of x, okay, we can also represent it in this form where you can write as ck of x square, right? So here x square basically is the difference calculation as we see over here. So if we are making, if we are considering the radial symmetry of the kernels, then this general equation which we saw earlier can be further improved, or it can be further refined in this particular way, where you're just trying to replace kx by this particular value, right? And so this would be the expression for the radially symmetric kernel. Okay, now we'll try to find out what is the relation which we have between the kernel density estimation and the mean shift vector, which we have studied earlier. Okay, so what we do here is first we have this particular equation of p of x, right, which we've discussed in the previous slide, where you're considering a radially symmetric kernel. So what we do first is we find the gradient of p of x, or basically we try to find out what is the first order derivative of p of x, right? And then in order to compute that, what we do is here this particular equation where you're trying to find out what is the gradient, or what is the first order derivative of k, which is the radially symmetric kernel, okay, which is a function of the distance between the current point as well as the of the current point with respect to the neighboring points, right? So here you can simplify this further. When you're taking the gradient, you'll get it in this form where you have x minus xi k dash into x minus xi here, which is the distance measured, right? Now we can simplify this further again, right? So you can just go through the steps later. All that you're doing is you have this expression over here, you take minus outside, so then that becomes x minus x, and when you're taking minus outside, you can represent this by minus k dash as a function of the distance. And if you're replacing minus k dash as a function of distance, and that one, if you're replacing by g of x over here, you'll get this particular expression, okay? And then again you can expand this further, okay? You can separate the xi and x and write it this way, and further when you're just rearranging, you'll get it in this particular form. So this here, this one, what you show or what is seen over here is the final equation that you have, right? So in this final equation, what we are observing is, now 1 by n c, these are all constants, and g of x minus xi square is also a constant, okay? So when I'm saying g, it is nothing but minus k dash of x, which means it is the negated derivative of the kernel, right? Since kernel is fixed, you have a particular standard kernel which you're using, you find that here this g function g would also be fixed, right? Fixed in the sense it would be a constant, right? So if you're looking at this part, what we see is, now this xi is nothing but the neighboring pixels or the contributing points that you're having, right? And this g function g over here acts as the weight, okay? So here again we are taking the average of those weights. So what we are doing is we are basically taking a weighted average in this case, okay? So this whole term over here represents the weighted average. We take the weighted average, okay, and subtract it from x, okay, which gives us a measure. And here what we have is again the constant values, okay, and this actually gives us what is del of p of x. Okay, so if you're looking at the final equation over here, after further just simplifying, okay, I can write it as del of p of x is equal to 1 by n to c sigma gi. Okay, sigma I is equal to 1 to n. If you have n points over here, xi gi by sigma I is equal to 1 to n gi minus x. And as I said, this one basically is the weighted mean shift vector that you have, right? So this term that you have is the weighted mean shift vector. Okay. Okay. Now, okay, one more point over here. Okay, so here the mean shift that you are considering, as I said, this one is the mean shift vector, right? And this is nothing but the gradient of your PDF. So what you can say is, and this part is a constant value. So what you can say is that the mean shift vector is nothing but the gradient of the PDF distribution that you're having. Okay, so just note that point. So what that means is, we have seen earlier in one of the slides when we were discussing about the mean shift vector, we saw that mean shift vector points, it always points towards the gradient of the density estimate, right? And this is a mathematical equation that shows the same, where it shows that this mean shift vector over here is nothing but the gradient of the PDF. Okay, now we can also represent the mean shift vector in another way. Okay, that is, instead of saying that the mean shift vector moves towards the gradient of the PDF, we can also say that the mean shift vector can be represented as maximizing this particular equation that you have, right? So in this equation, again, if you see, C is a constant over here, you have K, which is a kernel, X minus Xi, which is basically the distance measured. And along with that, you have it normalized with H. H is nothing but the circular region of interest, right? So if you're taking this equation and maximizing this, you can say that you're getting the, or what happens is that you're moving towards the denser region. So mean shift procedure, it can also be obtained by maximizing this particular equation that you're having. And as I said earlier, mean shift vector, what it does is it is trying to find out what is the maxima in a particular PDF, right? So here this H, it is the radius of the circular region of interest that we are considering. Okay. And when we are simplifying this, what we get here is that the maxima occurs at this particular point y. Okay, and this is the derived expression for that. Again, in the derived expression, what we see is the change that we see over here is that now in the weights that you are calculating, you also have it normalized with respect to the radius of the circular region of interest. Okay, other than that, it's the same. So here this y represents what is the location of the maxima which is present in the particular PDF, or the probability density function. Okay. Okay, so in reality, if you're looking at the mean shift vector, as I said earlier, in the mean shift vector, what happens is you initialize a particular circular region of interest, and from there we try to find the center of mass and keep moving towards the center of mass after each and every iterations, and finally you reach a particular center of mass where it no longer changes, right? I also said that it is irrespective of, or this works irrespective of where is the initialization. So in reality, what is done is we don't just take one particular initialization. We rather go for multiple initialization, as shown over here. Okay, we take multiple points within the particular data distribution, and what is done is parallelly all of these are run together. Okay, so parallelly all the mean shift algorithm is run together, and what happens is all of these would coincide to a particular location. Now as you see over here, it may not coincide exactly the same, okay, because definitely there would be some noise or some kind of problems which would exist. But what happens is that when all of these combine together, the common area which you see over here would be you can take from the result of all of these together to consider or to finalize which is the densest region. So finally, what we see is that we have identified that this particular spot, which is seen here, is the location of the maximum density, or it is the densest region. And therefore, all the multiple initializations which you had finally converged to a particular point, which is shown over here. Okay, so we'll stop here. What we had discussed today was we discussed about the summary matching, okay, and what is the basic idea of summary matching for object tracking. And we discussed how histograms can be used for used as a summary representation. And then we moved on to understand what is the basic working of the mean shift algorithm, and we saw that it can be used to find out the densest region of data distribution. And we also saw that the densest region of a data distribution can be correlated with the peak of a PDF or the probability density function. And we also saw some mathematical equations which shows the same. We also saw the weighted mean shift vector, wherein we apply weights to the different neighboring points depending upon its distance from the data point which is or what we are considering, right? So these are the different topics which we saw today. And the next topic is how we can make use of the mean shift vector in order to apply it for the summary matching. Okay, and that we'll continue in the next class. If you have any doubts, I can take it now.
Excuse me, ma'am.
Yes.
So while we were doing summary matching initially, you said that uh, the center of mass is calculated by taking the points inside the region of interest and then adding them up. So what exactly are we adding there?
No, not adding, we are taking the average over there. Okay, I'll just show you over here, right? Let me go
Yes.
here. Okay. Yeah. So here what we are doing is we are not just adding this up. We are trying to find out what is the average over here, right? So you have, let's say these data points are pixel intensity values. Now these data points can have any values. Let us assume it is pixel intensity values. So you take these pixel intensity values and you average them together. Okay. So by averaging that, you find it out. Now, as I said earlier, when you're trying to find the mean shift vector, you can either do the averaging in a uniform way where you consider that all the data points have equal contribution to this particular center of the circular region of interest, or you can also take a weighted averaging where you're saying that okay, from the center of the circular region of interest, I'm giving more weightage to the points which are lying nearby. Okay, when I'm taking the distance, okay, when it's the ones which are lying nearby as compared to the ones which are far away, and so on. So you can kind of give a weighted average, or you can give a uniform weighting. Okay, so those are different methods by which it can be calculated. But finally what happens is that by taking this weighted average, since the more data points are present over here, right, you'll get the average which is pointing towards the region where you have more data points which are concentrated. So by that, you find what is the mean over there, and you're trying to move the circular region of interest to that, from which you get the new circular region of interest, and you continue that process.
Yes, right. That's understood.
Okay.
Ma'am, another question was have like saying that two region of interests and then having their summaries matching. So we match their summaries based on histogram, right?
Yes, yes.
So how exactly are we looking at when we say that histograms should match? So
Yes.
there is a condition wherein the pixel values, like number of pixels for another value could increase, and certain like for some
Yes.
other pixel value it could decrease. The number of pixels could
Yeah.
decrease. So that way the histogram would be different. So how would we see
Yes.
that they get similar?
So yeah, I'll answer you. I'll answer your question in two ways. One way is two things. One point which I have to say is that the very next topic that we will be learning would be how we do the histogram matching with the help of mean shift vector or the mean shift algorithm which we have discussed. We will
Oh,
see that in the next class. Okay, and to answer your question regarding the pixel intensity values that the histogram will change, yes, the histogram will change. What we are looking for, or what we are saying, the cases that we are looking for is not when you have a very large change in the pixel intensity. Like for example, from a very let's say brightly lit room, you're suddenly switching off the lights and or so on, and it's very dim or so. Not that much of a change. Let's say there is only some slight changes, like for example when you have some kind of a blur, you can still see the person, but at the same time it is kind of a little blurred. So the blurring occurs because the pixel intensity values have kind of blended together with the neighboring ones, right? So it's kind of a little smudged. So cases like that, or certain cases where when I say illumination variations, what I mean is there are slight changes in the brightness level or overall exposure of the video. So basically the images that we are considering, or the frames that we are considering, it's a video sequence, right?
Yeah.
So what we are assuming is the background is more or less the same. So when I say background, it also implies the illumination in the background, okay? And we are assuming that that is kind of similar and there is not much changes. But if there are some changes, and because of which there are slight changes in the pixel intensity, the histogram will change. So even if it is slight intensity changes, the histogram still changes, because you will see that so when the pixel intensity is changing, you'll see that it is actually moving to the neighboring bins, right? It could be the next neighboring bin, or it could be a few bins apart, okay? But it may not be in such a way that it would affect the overall shape. Okay, the overall shape may not be exactly the same, but if you're looking at the envelope of the histogram, it would be more or less the same. Okay,
Okay.
that is how we are trying to find the similarity. So as you said, yes, there would be changes in the exact values of the histogram when there is a pixel intensity variation. But what we are looking at is the envelope or the shape of the histogram, which does not change much. And that is why we are saying the similarity score should be high. We are not saying that the similarity score should be exactly one. Like if it's normalized within a scale of 0 to 1, we are not saying that the similarity score should be 1 when you're trying to match the histograms. What we're saying is the histogram with the maximum similarity. And why we are specifying it as maximum similarity is because there would be changes in the actual histogram values, right?
Right. Thank
Yeah.
you.
Okay, is there any other questions? I see. Ma'am, how do we find the COM of the points? Prathamesh, can you expand COM? Center of, oh, okay, you mean the center of mass. Was it Prathamesh Sanjay who just asked, inquired with me right now? Okay, I hope I had answered this question earlier in one of the queries which has been asked. I hope it's clear right now. Prathamesh, you can respond in the chat if it's clear to you, or if it's any if there's any other question, you can just post that in the chat. Okay, so if there are no other questions, I'll just stop the recording right now, and it is time for quiz. So I'll just